Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on August 25, 2025, which was just 2 days ago. The big punchline is a new benchmark for condensed matter physics, where even the best models, Grok 4, reach only 36 average SEED score and 28% accuracy. The paper is titled CMPhysBench, a benchmark for evaluating large language models in condensed matter physics. And, as we will see, the implications for evaluation and training are quite significant. In short, the work introduces calculation-focused questions and a scalable expression edit distance metric that grants fine-grained partial credit and aligns closely with expert judgment. Also, the authors shared a GitHub repo. You'll find a concise README pointing to the CMPhysBench dataset on Hugging Face, a C directory for initialization assets, and a Python-focused codebase. It highlights stars and basic repo activity, but there are no releases or packages yet, so it's a lean starting point. Alright, the repo overview just showed where the data lives. Figure 1 now illustrates why the scoring matters. Figure 1 presents an Anderson SD model question and contrasts 3 graders: accuracy, expression edit distance, and the proposed scalable expression edit distance. The scalable expression edit distance parses equations into trees, so it assigns partial credit when a response matches structure but includes a small term, which yields a mid-score instead of 0. Accuracy gives all or nothing, while expression edit distance misjudges by over-rewarding superficial similarity. Alright, Figure 2 captures what the dataset looks like at a glance. Panel A shows 6 topic buckets with roughly even shares for magnetism, semiconductors, theoretical foundations, and others, while superconductivity and strongly correlated systems contribute smaller slices. Panel B highlights answer formats, where numeric dominates at about 2/3, so most tasks expect a final number rather than a derivation-only form. Panel C lists concrete examples, which clarifies tuple, expression, interval, numeric, and equation outputs for grading. So, Figure 4 extends the dataset overview by detailing how scoring actually works. Figure 4 shows the scalable expression edit distance pipeline. Equations and expressions become tree structures, so small local edits change the score proportionally rather than flipping to 0. The left panels illustrate 2 model responses, where a single added term yields a mild penalty, while a collapsed 0 side yields a severe drop. The right panels summarize rules for expressions, equations, tuples, intervals, and numeric answers, which include unit conversion and rounding tolerance. So the pipeline details just set the stage. Figure 5 presents head-to-head results across model families. The chart shows seed in light bars and expert accuracy in dark bars, which makes the partial credit gap visible because seed is consistently 5 to 9 points higher. A small lead cluster stands out. Grok 4 near 36 seed and about 29% accuracy, O3 slightly lower, and Gemini 2.5 Pro close behind. Most other systems sit in the mid-band near 23 to 28 seed, with roughly 16 to 20% accuracy. Wrapping up, 2 takeaways stand out. First, graduate-level condensed matter problems expose a sizable gap, with top systems near 36 SEED and under 30% accuracy. Second, the scalable expression edit distance offers reliable partial credit that tracks expert judgment, enabling sharper diagnostics. The broader implication is clear. Progress needs physics-aware training and symbolic tooling. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.